Unlocking the secrets of dark matter, a new particle model. We've been hunting for the universe's biggest ghost for nearly a century, and we still have nothing to show for it. Dark matter, the invisible substance that makes up a staggering 27% of the cosmos, remains one of science's most profound mysteries. But what if our search has been hampered because we've been looking for the wrong kind of interaction all along? A groundbreaking new theoretical model, developed by a team of physicists at the University of Sao Paulo, our work explores the possibility of a dark sector filled with light particles that only interact very feebly with the familiar particles of our world, which are described by the standard model of particle physics. For years, the prevailing wisdom pointed toward massive, heavy particles, often called WIMPs, as the prime candidates for dark matter. The hope was that powerful machines like CE, Dark Matter Origins, Mirror World, and Universe's Edge explained. Dark matter mysteries have long captivated scientists, and the latest research by Professor Stefano Profumo from the University of California, Santa Cruz, is stirring up fresh debates on its origins. In two thought-provoking studies, Profumo tackles one of modern physics' most enduring puzzles. What exactly are the particles that make up dark matter? The first study, published on July 8 in Physical Review D, delves into the possibility that dark matter could have formed in a hidden sector, a sort of mirror world that hosts its own particles and forces. Imagine a shadowy universe governed by similar physical laws to our own, but completely invisible to human detectors. Inspired by the well-established theory of quantum chromodynamics, QCD, which explains how quarks bind together to form protons and neutrons, Profumo proposes a parallel dark QCD scenario. In this framework, dark quarks and dark gluons come together to form heavy composite particles known as dark baryons. Under the extreme conditions of the early universe, these dark baryons might have grown so dense and massive that they gravitationally collapsed into minuscule, stable black holes or similar objects. Although only a few times heavier than the Planck mass, the basic unit in quantum gravity. If produced in sufficient numbers, these remnants could account for the entirety of the dark matter we observe today. But here's where it gets controversial. Such objects would interact solely through gravity, making them undetectable by conventional particle detectors. Yet, they would have a profound influence on galactic formation and the overall structure of the cosmos. Profumo's second paper, released in May in Physical Review D, turns attention to another fascinating possibility: the creation of dark matter through processes at the cosmic horizon, which is conceptually similar to the edge of a black hole's event horizon. He asks a bold question: could a brief period of accelerated expansion in the post-inflation universe have radiated particles into existence? By applying principles from quantum field theory in curved space-time, his work demonstrates that this mechanism could produce dark matter particles across a wide array of masses, depending on the temperature and duration of this enigmatic phase. Notably, this theory makes no assumptions about the interactions between dark matter and ordinary matter, only that the dark matter is stable and produced via gravitational effects. In a sense, it echoes the idea that observers near cosmic horizons might detect thermal radiation emerging from quantum effects. Both studies venture into speculative territory, offering self-contained and calculable models that step away from traditional particle dark matter approaches, a necessity in light of repeated null results from experiments designed to detect conventional dark matter candidates. Profumo, who also serves as Deputy Director for Theory at the Santa Cruz Institute for Particle Physics, has a long-standing history of bridging cosmology and particle physics. His influential 2017 textbook, An Introduction to Particle Dark Matter, encapsulates many of the lessons learned from decades of research in this field. Revolutionizing dark matter detection. New inelastic model breakthrough. Imagine a universe where dark matter, that elusive and mysterious substance, is finally within our grasp. A groundbreaking model proposed by a team of physicists at the University of Sao Paulo's Institute of Physics might just make that a reality. This innovative model describes the behavior of dark matter in the presence of dark energy, aligning perfectly with current astronomical observations. But here's where it gets controversial. This model suggests that dark matter could be made up of lightweight particles that interact through a massive vector mediator, offering an alternative explanation for the remnants of dark matter in the universe. And this is the part most people miss. This framework could potentially bypass the experimental challenges that have kept dark matter hidden from us until now. The findings, published in the Journal of High Energy Physics, have the potential to revolutionize how we conduct particle physics analyses in the future. Now let's dive into the specifics. The researchers have introduced a new model where a heavy, stable form of dark matter. The model involves a light mediator called ZQ, which acts as a portal connecting the dark sector with the standard model SM particles. These ZQ-induced vector mediators facilitate direct interactions between the dark sector and SM particles. The black line in the parameter space indicates where dark matter might be hiding, unobserved, and this is something future experiments will need to address. The study suggests a shift in our approach to searching for dark matter. Instead of focusing on the discovery frontier, where highly sensitive instruments scan for signals, we should pivot to the intensity frontier. This approach seeks ever finer measurements to uncover anomalies. Future experiments will delve deeper into these unexplained aspects of particle physics, armed with new online tools designed to shed light on the mysteries of dark matter. So what do you think? Could this new model truly revolutionize our understanding of dark matter? Or are there still too many unknowns? Share your thoughts in the comments below and let's spark a discussion on this fascinating topic. Perhaps this model could be the key to unlocking the secrets of the universe. Or maybe it's just another piece of the puzzle. Either way, it's a step forward in our quest to understand the cosmos.